So let me just remind you of a couple of things that we have seen yesterday. Well, we were studying operators in n equals 4 super-Young mills. We were computing the dimensions of these operators in n equals 4 super-Young mills, which are dual to the energies of strings in AdS 5 times S5. So we were roughly producing data for these operators at weak coupling. Okay, so we were computing, understanding how could we in principle compute these operators, these dimensions. And we understood that there were two obvious ways of proceeding. One way, at least two, there are many of course, but there are at least two. One by studying 4-point function of operators in the field theory. And they tell you about everything that has a non-zero 3-point function with those operators that flows in between. And by using this, we could read the anomalous dimension of these operators to the first few loops. And the other approach was to study the renormalization of the operators, to understand how do we need to mix them, to renormalize them, by computing their mixing matrix. Now, because of planarity, the mixing matrix, which is the matrix between 2-point functions of operators, the operators must be almost the same, except for maybe some interaction at one loop between neighbors, some interaction that might involve next to nearest neighbors at 2 loops, and so on. And we saw what was the form of this matrix that you could always represent, if you wanted, as some kind of spin chain, because the trace is a one-dimensional structure. And we saw that if we have, for example, operators just made out of 2 of the complex scalars, z's and x's, respectively, then we end up with the Heisenberg Hamiltonian, that has basically one term where nothing happens to the neighboring spins, and one term where the spins can hop, where an x can hop to where it was a z. So this is what's called the hopping term. Then we consider the operators with derivatives, which are contained in particular our operator OS that we were studying, our spinning operator. And those can be represented by a non-compact spin chain, where at each side of the spin chain we have an integer that runs from 0 to infinity that tells you how many derivatives you have, how many light cone derivatives you have at each side. For example, this Hamiltonian acting on the first 2 sides, it would give one term that gives back the same thing without any hopping, and one term where some derivatives can jump from the second operator to the first, or from the first to the second, and this is what's called the hopping term. So you can think in both cases that you have some kind of vacuum, just z's, and then the x's are hopping right and left on your spin chain. And here the same, you could start with many z's and then just a few derivatives that are hopping. The difference is that here the particles are not hardcore. They don't mind being on top of each other. So the 2 derivatives, you can have 2 derivatives in the same place, whereas you cannot have 2 x's in the same place. Okay. Then in the exercise, you were asked to check that indeed the Hamiltonian acting on this state was just giving harmonic number times the state. Okay? Which in practice, if you compare now component by component of this wave function, amounts to proving an identity like this. So if you have probably with some binomial here, sk, I think. Let me check. That is, if you have the eigenvalue times the wave function, and the wave function was just binomial, s choose k times -1 to the k. Okay? So I remind you that when written in terms of a trace, there was a square, but I use one of the powers to just define my cats. So this has factorials here. So what we have to show is that the wave function times the eigenvalue is equal to the action on the neighboring wave functions, whatever can generate that wave function term. So you can start with the wave function already, or you can hop to the wave function. Okay? So this is the kind of identity you have to show, that this is 0, that this stuff is equal to this stuff. Okay? Was there any trouble showing this? Or verifying this, or checking this? Did you reach the point where you wanted to check this? Yeah? Okay, and it was okay. Okay, then I don't give any comments. Okay. Very good. So, what other comments do I want to make? So here we have some operators, and they are dual to some strings, but there are many operators, and there are many possible strings. So how can we get some hints about what kind of string solutions are we considering? Well, one way, not the only way, and definitely not the most efficient way, to tell you what would be the most efficient way would require a few lectures. But let's try to just heuristically understand that these operators here, they have a lot of spin. Right? If you put lots of derivatives. So if you put lots of derivatives, these guys here, so if you take lots of derivatives, that is S, which is the total number of derivatives, is much bigger than J. Let this J be an order 1 number. Then what you will be describing is a string that, because it has a lot of spin and it's inserted at the bottom of the cylinder, it's spinning like crazy in AdS. It's rotating a lot in AdS. And because it has very few units of R charge, which is the charge that measures the rotations in the sphere, therefore it's associated by another theorem to angular momentum of the string. It has very few angular momentum in the sphere. So in the sphere, because it has very low charges associated to this symmetry, that is very low angular momentum, it's doing very little. It's some boring, almost point-like string moving very slowly in the sphere. Okay? This is matching the charge, which is J, with the charge in string theory, which is angular momentum, the charge associated to rotations in the sphere. Is it clear? On the other hand, these kind of operators are very different. These ones, they have no derivatives, okay? But they can have many J1, which is the number of X fields, say, and J2, which would be the number of Z fields. Then this would correspond to a string that is boring in AdS. It's just moving in the center of the box as a point particle. And in the sphere, it would be spinning like crazy, because it will have lots of angular momentum. Okay. So J1 and J2 would correspond to rotation in two planes. Remember that X was a combination of two scalars, and Z was a combination of other two scalars. So having a lot of X's means having a lot of angular momenta. So remember, so you have a sphere, so you have 6 directions where the 5 sphere is embedded. And having lots of X's means having lots of angular momenta in the corresponding plane. So this is the number of, say, I don't remember. I think I called it phi3 plus I phi4. And this was the number of phi1 plus I phi2. This was the definition of Z. So you have a sphere that is embedded in 6 dimensions, x1 up to x6. And this J2 would be the angular momentum of the string in the plane x1, x2. So angular momentum in the plane x1, x2. And this would be related to the angular momentum in the plane x3, x4. It's associated to the symmetry that rotates those directions. And then, if you have an operator that has a lot of fields and a lot of derivatives, it will be dual to an operator that is moving non-trivially, a string that is non-trivial both in AdS and in the sphere. It will be the most generic situation. It will be a string that is excited both in AdS and in the sphere. Okay? Is it clear? Okay. Any questions so far? Okay, I want to make one more comment about this vacuum spin chain. So the spin chain here, where you have just trace of Z to the L, or trace, just trace of Z to the L. Z many times and nothing else. Trace of Z to the L, which is just a spin chain where all sides are up, okay, corresponds to the ferromagnetic spin chain vacuum in the spin chain language. What is the anomalous energy of this state? Well, let's see. So we act on just spins up. So acting on a pair of spins up with either the identity or the permutation, it does nothing in both cases. So this state has zero energy. So it has no anomalous dimension. And in fact, the anomalous dimension at any loop order for these states are equal to 0. These are what are called states that are protected by supersymmetry. But here we see very explicitly that at one loop at least they are 0. Okay? And it's possible to show that they are 0 to all loop orders again by using, this is a consequence of supersymmetry. Okay? Okay, very good. So, in particular, trace of z is as gamma 1 equals 0 again. But if I rotate it, if we rotate the state, so we use a symmetry that rotates the scalars into themselves. In other words, in the spin chain language, we act with a lowering operator in SU2, which is an operator in SU2, it commutes with SU2 Hamiltonian. Right? So if we rotate the states, that is, we act with S minus in the spin chain language, we end up with a state that has trace z, x at some position, z, at some position n, and we sum over n, whatever it is. Okay? This corresponds in the spin chain language to acting with a lowering operator on the state where all spins are up. And this is a symmetry of the theory. Okay, so this is a symmetry. So the dimension of the new state, O nu. So the dimension of the operator O nu is equal to the dimension of the operator O. Or in the spin chain language, the Hamiltonian has SU2 symmetry. So the SU2 generators commute with the SU2 spin generators. This is the statement that some Hamiltonian has some symmetry. And in particular, at least at one loop we see it very explicitly, but again, everything I'm saying holds at any loop order. Trace of z times x is protected, has no anomalous dimension. And similarly, if you just rename the scalars, zx bar, z bar y, this is just different names for the scalars, so of course nothing changes, and z bar, y bar, they are all protected. Okay? And I remind you that this was one statement that was left to be proven when we used this approach of computing 4-point functions using these operators. So this is protected, C 4-point example. Okay, where we use that these external operators were very simple operators. They get no anomalous dimension. The guys in the middle do. So the correlation function, we see signs of anomalous dimension. We see logarithmic divergences. We see logarithmic singularity. We see stuff which is quantum and not protected flowing. But the external guys are protected. They are protected by supersymmetry. Okay. Now, the string trace z to the L is dual to a string with j units of angular momentum around the equator defined by the plane x1, 2. That is, we have the 5 sphere. Let me draw just x1, x2, and let these x's be all other x. So here I cannot draw a phi sphere, of course, so this is the best I can do. So this guy has angular momenta in this plane and in this plane only. So it's dual to some string that has some angular momentum along this equator. And the only thing it could be, if it's only in this equator, it's a point-like string. It's a string that trends to a point. It doesn't depend on sigma. It just depends on tau. And that is rotating around the equator. Nothing else. So it's just a point-like string moving around the equator. And in the cylinder, it's doing nothing. It is just standing in the middle of AdS, quiet. A point-like string moving in the middle of AdS. Okay? So it's given by T equal tau. Okay, so T of sigma and tau. The AdS time is just equal to tau. There is an angle here. Let's call this angle psi of sigma and tau. I can parameterize it just tau. Okay? And the other coordinates are equal to 0. Okay, or if they are angles, or pi over 2s, if they are just some angles that parameterize the sphere. But they are some trivial values, fixed values. So it's a string that is moving at the speed of light from the 10-dimensional point of view. It's moving in time and rotating around the sphere at the same time. And it is just a point-like string. The energy of a point-like string rotating with angular momentum j is just equal to j. This is just a very easy exercise. I think maybe you even did it, some similar exercise in your string theory lecture, but it's very simple to see that the energy of a point-like string rotating around the equator is just equal to j. This is a classical result. Okay? And it's the dual statement to the statement that this operator delta, the dimension is just a number of fields. And here we are saying that there is 0. These are the quantum corrections. Okay, so it's good that at least at strong coupling to leading order we find j. And here the claim is that we have 0 if we now consider the string quantum corrections. Okay? So for this particular kind of operators, the dimension as function of the coupling in AdS CFT, it's a very simple curve, just a straight line. Not the most exciting curve, but it does match between weak and strong coupling. We just get j in both cases. Yes?
Should it be trace of z to the j, do you mean?
Yes, sorry. Yeah, j is equal to L. Or did I use j already somewhere? Okay, I can use j here, right? Is there some L somewhere?
On the left.
On the left, here. Yeah. Thank you. Thank you. More questions? So this is the first example of a curve that interpolates all the way between weak and strong coupling. Okay? It's not a very exciting curve. Okay? It just starts at j, goes to j, and it doesn't move. It doesn't have any exciting minima or something in the middle. It is just fixed to be j. But it's still quite a non-trivial check, the fact that from Young-Mills, you predict that there are some operators whose energy is exactly j. So you know that you must end up with some strings that must have classical energy exactly j. And indeed, you go and you work out the simplest one that just moves in the equator, and indeed it has energy which is just equal to its spin. So this is what is called the BMN string that was found by authors whose name starts by BMN, Bernstein, Maldacena, and Nastase, in '98, I believe. Well, it's, if you want, the simplest string solution that you can have. Now we move to a more interesting one, which is a solution that, as we said, we'll consider a folded string that is rotating. Okay? It's rotating in AdS and drawing some kind of helix. But I don't think I should try to draw it. But you get the picture, right? Some string that is rotating and drawing some kind of helix in AdS. Okay? Very good. So this is the one we want to consider. That should be the dual to the operators with spin that we saw before. Okay? That should be the dual of our operators with some spin s. Okay. So now, let's then study this string solution. And we will use Nambugoto, as I said. So we write the action. Let's write the metric, the metric first. ds square is minus dt square cos square of rho plus d rho square plus sinh square of rho d omega of the 3-sphere. Okay? So how should we draw this? So rho is the radial direction here. Time is already represented in this picture. And then these circles here are a 3-sphere. But again, we only want to consider this folded string. So we are only going to use an equator, S1, inside S3. And we are going to parameterize it using this angle phi here. Okay? The same way that there we only use the angle psi and nothing else. Here the same thing. So let's just write the metric of this 3-sphere, and let's write what this angle phi is. So you can write a 3-sphere. What is a 3-sphere? It's a set of points such that x1 square plus x2 square plus x3 square plus x4 square is equal to 1. So it's an object that can be embedded in 4 dimensions. So a nice way of writing a metric is to just consider the flat metric on Euclidean 4-dimensional space when you put a parameterization that solves the sphere constraint. Okay? So this you know, I mean, I think you all know very well, but let me do it quickly. So you just write x4 equals sine of theta, x3 equal cosine of theta, sine of psi, x4 equal cosine of theta, cosine of psi, sine of phi, no, x2. And x1 equal cosine of theta, cosine of psi, cosine of phi. Okay? So you see that if you do, let's do the square of all these guys. This guy square plus this guy square gives this term square plus this term square, and the phi disappears because sine square plus cosine square is 1. Is it clear? If you do the square of these last two, the phi disappears. Then you add to it the square of this guy. Then the chi disappears. And then you add the square of this guy, and the theta disappears. And you get 1. Okay? So it's very easy to see if you do it nested. You do first this, then this, then. Okay, and when you do it, the metric, this metric here, in these variables, just becomes d theta square plus cosine square of theta, d chi square, plus cosine square of chi, cosine square of theta, d phi square. Okay. And this actually is just d phi square when we consider the equator, okay, where theta is equal to chi is equal to 0. Okay? Which are constant, of course. They are constant, you draw up all its differentials, and you keep just d phi squared. Okay? So this metric here becomes just d phi squared. Then, what we are doing is, what's our Nambugoto action? Well, our Nambugoto action contains some tension, square root lambda over 2 pi, or let's even do it a bit more slowly. Let me remind you that this metric comes multiplied by some L squared that sets some scale. Then the Nambugoto action is 1 over 2 pi alpha prime integral of square root of the determinant in the indices alpha and beta, okay, where alpha and beta take the values sigma or tau, in other words, 0 and 1, of the metric, which is G mu nu, where G mu nu is this metric, so this is nothing but G mu nu dx mu dx nu, G mu nu d alpha x mu d beta x nu. Okay, or maybe better to put, it's the same, doesn't matter of course, but just to be more close to what I wrote there, let me put the indices like this. Determinant of this object. Okay? So this describes the area, the area of the string. The area swept by the worldsheet of the string as it's moving in AdS. So distances are measured with the AdS metric. So you have seen this in your lectures, except that you were using the flat metric here. Right? But now we are in AdS. Okay. And if you say that this G is L squared times some small g, you take out the L, then you see that it is equivalent to putting here square root lambda over 2 pi when you take some L, and then you use here this small g mu nu. Okay? So you can replace just equivalent, and then you get a nice dimensionless parameter, which is the some dimensionless tension, which is related to the 't Hooft coupling of n equals 4. Okay. Now we plug an ansatz. So now I remind you that this matrix G mu nu, now all we use is theta, rho, and t. Okay? These are the only relevant coordinates. But now let's see, what do we have? So we have here a folded string. So let me already mark here 2 points, and let me make the following observation, that this string is made of 4 equal halves. Part 1, part 2 on the other side, part 3, and part 4. Okay? Or not just an observation, because I'm close to the picture. Okay? It's made out of 4 parts that are the same. Is it okay? And then what ansatz do we want to make? We want to study a string where rho depends on sigma, the coordinate on the worldsheet, where t is a function of tau only, and where phi is just a function of tau. In other words, it's a rigid folded string. That's a solution we want to look. Not for a folded string that is rotating and bending at the same time. It rotates as a rod. So phi only depends on tau. Okay? And now we plug that ansatz here. Okay? We plug that ansatz here. So we get that this matrix here becomes, let me use the small metric G. So this becomes the determinant, okay, where I have from rho, it's the only guy that depends on sigma. So the component 0, which is sigma in this notation, is just rho prime square in the determinant. There's nothing that depends on time and sigma. They either depend only on time or only on sigma. So there are no off-diagonal elements in our matrix. Is it clear? Because things depend either on time or on sigma. And what depends on time? Well, the angle phi and time t. So we have, for the angle phi, we get phi dot square times sinh square of rho. And for time, we get t dot square times cos square of rho. Okay? And I put an overall minus sign because of the signature. And dot stands for derivative with respect to time, and prime with respect to sigma, as usual. Okay. Is it clear? Very good. So the Nambu-Goto action becomes some integral d sigma rho prime factors out. It appears inside the determinant square, so you can take it out of the square root. Okay, times square root of t dot square times cos square of rho minus phi dot square times sinh square of rho. Okay, and this part I notice. Okay, and there is some square root lambda over 2 pi. And this part, let's notice that we can write it in the following way. We can say, let's make a picture seeing the cylinder from above or from below. And we have some folded string here. Okay? And let this distance here be rho 0, the maximum value that the string stretches. Okay? This angle here is phi. Okay? And then this stuff is nothing but 4 times, 4 because each segment, there are 4 segments that contribute the same, of course. So 4 times the integral from 0 to the maximum value if we change from sigma to the variable rho itself. Right? We can actually do the following. We can actually also take out t dot. And let me divide here by t dot square. Okay? So then, and there is some d tau here, sorry. And then all this I can write as just d rho dt. Now we consider the situation where derivative phi dot over t dot, which is nothing but the derivative of phi with respect to the global time t, where the string is rotating with some frequency omega. Okay? So in other words, we are saying that phi is equal to omega times the AdS global time t. So from an observer in global AdS, I'm not committing to any parameterization tau, and I'm not committing to any parameterization sigma. And that's okay, because Nambu-Goto is parameterization invariant. The way we choose to parameterize our surface is just our choice. Of course, what matters is the area of the surface. Right? This you saw at length during your lecture. So this integral over t, nothing actually depends on t. This is just some constant frequency. So this integral over t just gives some overall time, if you want. So it doesn't matter. In other words, if you just consider the Lagrangian, am I right that the action is integral dt with the Lagrangian? There's something which is when you remove the integral over t only. Is it called the Lagrangian? And then Lagrangian density is what we normally call Lagrangian, right? Okay, very good. So then the Lagrangian, okay, I remind you that the action is integral dt of the Lagrangian by definition. So then if you forget about the integral in t, just to compute the Lagrangian, it is equal to square root lambda over 2 pi for integral d rho 0, d rho from 0 to rho 0 to the maximum value, square root of cos square of rho minus omega square sinh square of rho. Okay. Any questions so far? Okay. So, and again, this is nothing but integral d sigma. Let me write it once with d sigma because it's going to be useful for what I'm going to do now, times rho prime. Now we compute the equations of motion following from this section that tell you what? It's an action that only depends on sigma, derivative with respect to sigma of the derivative of the Lagrangian density with respect to rho prime is equal to the derivative of the Lagrangian with respect to rho. Well, derivative of the Lagrangian with respect to rho prime just gives the square root. Okay, so this just gives d sigma of the square root, the first term. And the second term, derivative of the Lagrangian with respect to rho, just gives rho prime, that is outside the square root, times the derivative with respect to rho of the square root. So the final equations of motion that you get are the following. Rho prime over square root of cos square rho minus omega square sinh square rho is equal to 0. Give me 1 second because I'm a bit confused by something, but I know this is correct for sure, but I'm a bit puzzled by something. No, it should be okay. Very good. And from this equation, it's clear that there is a value where the square root vanishes, which is the value where rho prime can vanish. So rho prime will vanish, the point where rho will reach a maximum, so rho prime equal to 0, at the value given by at rho 0, such that omega square times tangent hyperbolic square of rho 0 is equal to 0. So this is how we determine the relation between the maximum value of rho and the frequency by which the string is rotated. Right? Is it clear? So this just tells you that, of course, there should be a relation. The more it rotates, the more it opens up by centrifugal force. The less it rotates, the closer to the center it should be, because the AdS is a box. So we see indeed that if omega is very large, rho needs to be very small to compensate. If rho is very large, no, wait. If rho is very large, rho should be very large. Sorry, I have something wrong here. Give me 1 second. Okay, so actually this statement is not correct. Okay, sorry. This is a correct statement, but please ignore what I said afterwards. This intuition of fast, not fast is also dangerous because okay. let's ignore this quick interpretation that is a bit naive because it ignores the fact that we are in a curved spacetime and our intuition sometimes can be tricky. Okay, so we have a relation that tells you what's the frequency, what's the relation between the frequency and the maximum value that the string reaches. And we have an expression for the action in terms of rho 0 and omega. And now we compute the interesting physical observables that are the nether charges with respect to the symmetries. So the energy is the nether charge with respect to translations in time t dot. So we go to the original action and compute the corresponding nether charge, and we get what? Square root lambda over 2 pi times 4, because each segment contributes to the same in the same way. Integral of cos square of rho, which is what multiplies the t dot, divided by the square root. And the spin is the variation with respect to the angle. So we take the variation with respect to the angle, so it produces a sinh square of rho times the frequency omega, which is phi dot, divided by the square root. And these integrals, they run always from 0 to rho 0, and here from 0 to rho 0. Okay? So what we have now, this is the spin, which is associated to rotations in angle phi. And this is the energy, which is the symmetry associated to time translations. So the problem is now in principle solved because we have energy that depends on rho 0, but rho 0 is just function of omega, and it also depends on omega. And we have the spin that is again a function of rho 0, but rho 0 is fixed by omega and also a function of omega. So that means that in parametric form we have the energy as function of the spin. Okay? Is it clear? Yes?
Is the equation of motion correct? Because it seems to be saying that rho prime must be 0 always.
I might have a wrong sign somewhere. No, this equation of motion. Yeah, this equation of motion probably not correct indeed. Yes. Tak. I guess that there is a 1 here, but I would have to think a bit carefully. Let me see. Give me 1 second. Yeah, the equation of motion cannot be right indeed. Thank you. Yeah, it should be 1. Indeed. I had a typo in my notes. It should be 1. But I confess I'm a bit puzzled. I don't see it immediately, but I'm too close. It's true. You can check. You can find the typo later. Right, so it's 1. So okay, at least it makes more sense that rho prime is proportional to the square root. So it vanishes indeed when the square root vanishes. But I'm doing something embarrassingly wrong with the equations of motion that I will find and tell you tomorrow. I don't. But I mean, I hope the physics is clear. There is some sign problem, but I don't. But we should not care much, provided we understand the physics, which tells you that we have now the energy and spin as function of the spin completely determined. And now let's do some consistency checks and see that what we are getting makes sense. So now we want to consider 2 limits. Okay. one limit which is small spin, and another limit that is large spin. Okay. So actually, by small spin, we actually mean the following. Spin is naturally measured in units of h bar, and the coupling is square root of lambda. So what we want to say is that the appropriate variables, you see that the action scales with square root of lambda. So all charges scale with square root of lambda, the string tension, right? So the natural charges to work with are energy and S measured in terms of square root of lambda. And we can define in this way some curly S and some curly E. Okay. And what we mean by large and small spin is rather in terms of this curly sense. That's the only parameter that appears. So it's much smaller than 1, or curly spin much bigger than 1. Okay, so what I want to say is that we take some macroscopic spin. The spin is rotating very fast, the spin is large, but the string tension is also large. So by taking small spin, we don't mean that we have some quantum string with 1 or 2 quanta of angular momenta. It has a big number of angular momenta, but still but it's a small classical number, like it's order 1 but small, 0.1, 0.01, something like that, or it's very big. Okay. So, and they will correspond 1 and 2, of course, to the case, of course not, because our intuition was already a bit anxious, but they will correspond, as we will see, to short strings or to long strings. Okay? But this we will see. I'm not assuming. So let's suppose that rho 0 is very small. But when is rho 0 very small? Rho 0 is very small if this omega is very big. This was what the equations are telling us. So omega needs to be very large. Then, indeed, if omega is very large, rho 0 is approximately equal to 1 over omega. Right? Is it clear? Yes? Then you can expand all expressions at small omega, at small rho. So you can expand the square root and so on. You can expand everything. Okay? So, okay, our intuition tells you, and we don't feel the box. So we expand the results. Okay? So we see flat space. We are at the center of the box. We don't feel its curvature. Okay? And you can just expand, say, the square root becomes 1 minus omega square rho square, for example, in this limit. Okay? And so on. You simplify these equations. You replace omega 0 by this. And you get that the energy, when you expand in this limit, okay, is equal to pi over 2 omega, and that the spin S is equal to times 4 square root lambda over 2 pi. And the spin S is equal to pi over 4 omega square for square root lambda over 2 pi again. Okay, so the 4 and the square root lambda comes just from the action. And this pi over 2 omega and pi over these two results are just what those two integrals there for the other charges give in this approximation when rho 0 is approximately equal to 1 over omega and it's very small. So now you see that you have both E and S given explicitly in terms of omega, so you can write immediately what is the energy in terms of the spin, and you find that it can be written as saying that the energy measured in these units of square root of lambda, if you divide by square root of lambda, is square root of 2 times the spin measured in units of square root of lambda. And this is exactly what you know in flat space from the leading Regge trajectory, that energy square goes like the spin. Okay? It's funny, I mean, I'm a bit puzzled, but it's true for sure. But you see that when the spin is small, the frequency is rotating very fast. Maybe the way to think is that the object is small, so because the object is small, it can rotate very fast, whereas if it's big, it's hard to make it rotating very fast. So, I mean, at least it's what we are seeing explicitly. Okay. So as in flat space. Okay, so this was the first case where we have short strings. What about the second case where we have long strings? For long strings, we want rho 0 to be much larger than 1. But the only way rho 0 can be much larger than 1, and again, I did a mistake. What did I write there? Not equal to 0, equal to 1. Oh, the square root is equal to 0 when these two terms give the same. So the ratio of them is equal to 1, not 0. Right? And that's why rho 0 was equal to 1 over omega when omega was very large. So now rho 0 is very large, so the tangent hyperbolic goes to 1. So it seems that this is what happens when this frequency omega goes to 1. So indeed, if we now write an ansatz, omega equal 1, slightly more than 1, because tangent is slightly smaller than 1, 1 plus 2 eta, and say that eta goes to 0, then if you try to solve, it's easy to see that rho 0 will be log of 1 over eta, maybe some factor of 2 probably, right? Because the cosh, you keep only one of the exponentials. 1/2 log of 1 over eta in this limit. Okay? Okay? Then you compute the energy and the spin, now that with this relation between omega and rho 0, and you get that the energy diverges when this eta goes to 0. It becomes square root lambda over 2 pi, okay, times 4 probably, even though I don't have it in my notes, so I will remove it, I don't know. Okay, I'll put it, I don't know. And then there is, it diverges when eta goes to 0, 1 over eta, and if you compute the next correction, it gives log of 1 over eta. This is when eta is going to 0. And for the spin, you find a very similar expression with just a different minus sign. So again, from reading both, we can now compute the energy as a function of the spin. Okay. That should be no force. It means that the result gives 1 force. Okay, so again, is it clear? I mean, it's just a technical computation now, expanding those integrals at large values. Okay. By the way, I should say that I'm considering these limits because they are the ones that are relevant physically. But this integral there, the integrals that I'm writing, they are all solvable exactly in terms of elliptic functions and so on. So you can solve this problem exactly in parametric form. But okay, it's not very instructive. What you want is to study the two limiting cases where you can extract the physics and see what's going on. Okay? But if you want, this integral is like these pendulum integrals, right? These pendulum problems. You can compute them and it gives you some elliptic Jacobi function or something like this. So you can do it at any parameter and then plot and check everything that I'm saying here. Okay? Very good. So this is the relation. And you see that this relation implies that the energy minus the spin, remind this was the twist, okay? The logs cancel, and you get square root lambda, what does not have a log cancel, square root lambda over pi times log 1 over eta. But eta to leading order is the spin plus corrections. So if I use that, I conclude that energy minus S equal square root lambda over pi log S plus correction. Is it clear? And this is the most important result I wanted to show you today. So we see that indeed, very non-trivially, the space is such that at very large spin, the dimensions of operators, the twist, indeed diverges logarithmically with the spin as we wanted. So I remind you that the claim was that in any gauge theory, delta minus S was given by some function f of lambda times log of the spin plus corrections at large spin. And this is indeed exactly what we obtain from a strong coupling computation. That the energy minus the spin is diverging logarithmically with the spin. Yeah? So the conclusion So this is exactly as expected. So we can start plotting something interesting. We can plot this cusp anomalous dimension f of lambda, which we said is a nice function to plot, as function of lambda. And we see it starts here, its life we computed yesterday, lambda over 2 pi square, which is the large spin limit of this energy here. It diverges logarithmically with S. Lambda over 2 pi square is what it gives. Then it has corrections. Yesterday I wrote to you some of the corrections. I believe the next one is lambda square. Actually, I don't believe. I don't know by heart. I think it's 3 over 8 or something like this, but let me confirm. No, lambda square over 96 pi squared. So you see it starts going up, and then it has some negative curvature. This is what we would get from weak coupling. So it starts going up, and then it bends a bit. Right? And at strong coupling, it goes to square root of lambda over pi, which is indeed a function that is also bent correctly. It's bent down, right? The derivative is going to 0 from above. And what we are seeing is the first signs of a function that wants to be glued. Okay? Okay, so this is what we are seeing now. So this was the weak coupling result. And what we computed today was the strong coupling, the leading order at strong coupling. Now, this guy here is one loop. This is 2 loops, etc. This guy here is a classical string computation. But then we can have quantum corrections. We can have one loop corrections here. Let me write to you what it is and give you a few words about how you would compute. And then you have more corrections. Now it's an expansion in powers of h bar, which at strong coupling is square root of lambda. And you get so it's an expansion now at large lambda. And let me check that I got this one right. I did not. Today I'm really sloppy. Okay. Let me tell you what this K is in a minute. That's not the relevant part. The relevant part is the structure of the expansion. And what's the physical meaning? How would you compute? This is now a one loop in string theory. And this is a two loops in string theory. That is, string theory is also a quantum field theory. And we can also start with some classical solution and quantize around it and compute the one loop determinant around this solution. And then compute the effects at two loops and compute this energy perturbatively in string theory at loop level. So the one loop in string theory, it's actually very simple. And you can think of it in the following way. This, you can think of the one loop energy in string theory around classical solutions in a simple way. How do we compute the quantum shift to the energy of an harmonic oscillator? What's the ground state energy of an harmonic oscillator? So you can do the harmonic oscillator, the energy is n times omega, which you can think as the classical energy. And then there is 1/2 h bar omega, which is the quantum correction. Now you have a quantum field theory. Quantum field theory contains infinitely many modes because it's a quantum field theory. Now the fields, you can expand them in modes and you have infinitely many modes. When you expand around the classical solution, all you care is about the quadratic action because you are expanding around the minimal surface. So you expand, the first derivative is 0, the second derivative is something. So you expand your action and you plug into your action some classical solution plus some delta x. And this will give some classical action, which is what we studied, plus some delta x, second derivative of the action with respect to x, delta x, plus dot, dot, dot. And this evaluated at the classical solution. And there's no first derivative because x classical obeys the equations of motion. Right? So we always get, by default, by definition, we get what's called the quadratic Lagrangian, which you can think of as infinitely many harmonic oscillators. Just this is what field theory is. When you have a quadratic field theory, it is just many harmonic oscillators. So all you have to do is compute this 1/2. So each contributes with 1/2 of the corresponding frequency, and you sum them all up, and fermions contribute with minus 1/2. Okay? This is just cartoonish, but just for you to have an idea of how you would compute. Expand the action around the classical solution. Read off what free particles you have, and for each particle, sum over all the modes. Okay? So for example, this minus 3 log 2 over pi, for example, comes from summing over the modes. So there is some integral, dp over 2 pi. And then when you expand, you notice that there are 5 modes in the sphere that have 0 mass. There is one mode in AdS that has mass 2. So I'm summing the energies of these guys with a 1/2, as we said, 1/2 for each mode. There are 2 modes in AdS that have mass square root of 2. And there are 8 fermions that have mass 1. Because of supersymmetry, this remarkable sum of infinitely many modes, because the fermions have this minus sign, this is a convergent sum. Otherwise, this would be very divergent, right? Imagine you don't have that minus 8 square root of pi square plus 1, it would be very, very badly divergent. The fermions save the day. This integral is given by some finite result, and that result is this minus 3 log 2 over pi. Okay? So this is just by take the action, expand the action around the solution we study, and you find some free action, and that free action describes 5 massless modes in the sphere, and describes there is one massive mode, one massive particle of mass 2, so that 2 square, mass square, 2 square equal to 4. And here there are 2 particles with mass square root of 2. And there are 8 fermions in superstring, and they have mass 1 around this classical solution. In total, you compute the sum 1/2 for each mode of the string, and you sum them all up together, and you get this first quantum correction. Okay? I'm not expecting you to follow the details, of course. Yes?
Is this related to the effective action of Q?
No, this is just computing the effective action. No, if you want, this is a way of computing the one-loop determinant around the classical solution. You are summing over all eigenvalues, and you can write it in this way. But the more generic way is, whenever you have a field theory and you expand around the classical background and want to consider the correction to the energy of the solution, right? You have some classical solution. You can think some soliton, like this string solution. And you want to compute a shift due to quantum effect. Now, what you know is that a classical solution, what's a classical solution? It's a solution that at the quantum level, you chose to excite some modes of your oscillators and left the other ones empty. Now, what's the quantum effect? The quantum effect is that an oscillator cannot really be empty. There's always 1/2 of omega. So you must sum for all the modes, including the fermions, the scalars, and so on, that play no role here. You must sum 1/2 of those. Even for the modes that you excited, you must still put the 1/2 of omega. So this is just quantum mechanics, if you want. So when you sum all these modes with the very important minus sign for the fermions, you get the correct result, which is this minus. You get this result, which is minus 3 log 2 over pi. This is a two-loop result in string theory. This is a tough result. This is a tough computation to do. A two-loop computation in string theory, it's not easy. Indeed, the first time it was done, it was incorrect. And only with much more powerful techniques that we will learn on tomorrow, we start tomorrow and learn mostly on Friday, it was understood that the result in string theory was incorrect, and then it was fixed. So this is a tough computation to do, and this guy is what's called the Catalan number, which I believe is around 0.9 or something like this. Maybe, or maybe not. I don't remember. I think it is. Okay, so we have a way of computing corrections at weak coupling. We have a way of computing corrections at strong coupling. But how can we ever check AdS CFT and compute a function at any value of the coupling? Right? Okay, something very hand-waving we can do. You heard probably about Borel resumming stuff, right? Starting to compute stuff in perturbation theory, assuming some analysis, try to resum this series and see, does it shoot here? Right? Or you can do more sophisticated stuff. You can, for example, try to fit a function that has the first terms here of your expansion, and that at strong coupling behaves like this leading order. And see if the fit naturally gives you something like this for the subleading, and then it will be a check that the function wants to be glued together. So you can do all sorts of numerology and checks, and if you would find spectacular agreement within a few %. But we want something better. We want to be able to plot this curve analytically. Now, this is quite a challenge. We see that the computation at weak coupling was not so trivial. It took us 1 or 2 lectures. The leading order at strong coupling was also not so trivial. And indeed, I will have to jump many intermediate steps to be able to plot for you on Friday the full result. But tomorrow I want to show you what's the key tool that is missing and that will allow us to do this absolutely remarkable thing that if you would ask like 10 years ago, no one would ever believe that you could compute a quantity in a quantum field theory at any value of the coupling. That would have been unthinkable a few years ago. And the technique that will come about to help, we already saw it briefly when we were discussing what kind of help could we get in simplifying our quantum field theories. And one of the things we saw that could eventually simplify a lot of quantum field theory was if we had integrability. Integrable models, which were models in one dimension where the scattering factorizes. And rather surprisingly, it turns out that integrability is exactly what will come to save the day and allow us for very powerful computational control over this observable. But we said that integrability, it could not be. Integrability was just for one dimension. Now we are studying a 4-dimensional theory. In 4 dimension, there was no such thing as shifting wave packets because otherwise particles would not scatter. So what am I speaking about? So how can it be that integrability can come to rescue? But it can, and it comes through a subtle way. It avoids this no-go theorem that you cannot have integrability in 4 dimensions by saying, no, it's not integrability for the S matrix. It's integrability in this subtle sense. First, you map 4 dimensions to 1-dimensional spin chains. Now that you are in the domain of 1-dimensional spin chains, you have these fields moving in this vacuum, this axis. Now they are 1-dimensional objects. They might be described by an integrable theory, who knows? And indeed, they are. So it's through this remarkable map that first you map 4 dimensions into 1 dimension, or into 2-dimensional if you count time. And then the 1 plus 1-dimensional theory will turn out to be an integrable theory. And because it is so, we know how to study integrable theories. We will do it, and then we will compare it with the results through more standard methods. Okay. So, any questions? I apologize for the sign in the middle. I'm really a bit confused by it. No questions? I'm a bit puzzled. People are asking very, very, very few questions. Does it mean it's very hard to follow? Or? Yes? Is it too hard? But then you should stop me. You should try to slow me down, at least as an exercise. Would you rather that I just slow down and repeat and explain again what we have seen so far? And I mean, I don't need to explain you this plot. I can just give more details here, and leave it for the future for you to learn about interpolation. Or I can move to the most exciting thing about gluing it or not. I mean,